So I probably could have told you this before I started the last video, but the last video where I taught you the definition of the derivative is an alternate way to find the slope of the tangent line to a curve at a given point, instead of using the difference quotient formula that we had already derived, it's not super important for calculus. Sorry. However, this video is super important. And it starts out with me kind of admitting that I've kind of sort of been lying to you all along. Maybe that's a bit strong. What I've been saying is that in Calc 1, what we're trying to do is figure out the derivative. That's true. The way I've been defining the derivative is it's the slope of the tangent line to a curve at a given point. That's mostly true. Really, the derivative in its full power is not the slope of the tangent line to a curve at a given point. It's the slope of the tangent line to a curve at any point. Instead of thinking about the derivative as a number, like a number that represents the slope of this line in purple, we want to think about the derivative as a function, as a mathematical machine that we can put any x value that we want into that will output the slope of the tangent line to that function at that point. So it doesn't have to be fixed at a point like x equals 2. Instead of thinking about f prime of 2 as the answer, we want to think about f prime of 2 as taking the derivative, this function, and evaluating it at the point where x equals 2. Did I just lose you there? Probably, but that's okay. The purpose of this video is to explain what the heck I'm talking about. What I'm saying is I gave you formulas like this formula here for the derivative. This is the difference quotient one, and then I also gave you the definition of the derivative one. And I kind of proved, I guess, in big air quotes through a few examples that they work out the exact same and give you the same answer. So far, we've been kind of starting with these formulas, but immediately changing all the x's into a number. Like if you want to find f prime of 2, our very first step was to change all the x's into 2's. What we're going to do in this video is we're not going to be looking for something like f prime of 2. We're going to be looking for f prime of x. We're going to use these formulas, but we're not going to change the x's into numbers. We're going to leave the x's as x's. If we do that, our answer won't just be some number. Our answer will be an expression involving the letter x. In other words, our answer will be a function, a machine that tells us the slope of the tangent line to the curve at any value x. And that is the thing that is super powerful. Let me show you how it works. F of x equals x squared minus 3x minus 2, and I want to find f prime of x. I can use either of these two formulas. It doesn't matter which one. Let's use the difference quotient because that's so nice. I'd want the limit as h approaches 0 of f of x plus h. If this is f of x plus h would be x plus h squared minus 3 times x plus h minus 2. From that, I want to subtract f of x. F of x is x squared minus 3x minus 2. Because I have multiple terms here, be careful with the parentheses. Make sure you're subtracting this entire thing. I want to divide that by the letter h. Is this a limit that I can evaluate? I mean, you could try, change all the h's into zeros, and you'll get 0 over 0. The same thing happens. What that means is there must be an h in the bottom that I can cancel with an h in the top. And there is. The only challenge is, because I have so many x's floating around, the algebra is going to be a little bit more challenging. But I think it'll be doable. Let's see. Let's get rid of all the parentheses. X plus h squared is x squared plus 2xh plus h squared. I'm going to do this algebra quickly, but hold yourself accountable. Pause it anywhere you're not sure and work these things out for yourself. Negative 3 times x plus h is negative 3x minus 3h. I got this minus 2, and then I'm subtracting all this stuff so I can get rid of the parentheses by taking the negative and distributing it through. You get negative x squared plus 3x plus 2. Wow, what a mess that is. Don't worry, it's going to clean up really nicely in the next step. And there's a nice built-in check, right? I know that this h has to cancel out with an h in the top. The only way I can cancel this h with an h in the top is if all of the terms in the top have an h in them. Right now, lots of those terms do not have an h in them. So I better be able to cancel out all of the terms that do not have an h in them. Does that happen? Well, let's see. I have a positive x squared here, but I have a negative x squared here. Oh, nice. I have 2xh here. That's got an h. I'm not too worried about it. I got h squared here. That's got an h. I'm not too worried about it. Minus 3x. No h's. That better cancel out. Oh, good. I have this plus 3x right here. Minus 3h. That's got an h. I'm not worried about it. Minus 2. That doesn't have an h. I sure hope that there's another term that can cancel out that minus 2. Sure enough, there is. There's this plus 2. When all the dust settles, all that's left up top is 2xh plus h squared minus 3h. Everything else went away. I divide that by h for the h in the denominator, and now things have gotten significantly prettier. I still can't change all the h's into zeros because I'd get 0 over 0, but I can factor in an h from each of these terms up top and cancel that with the h in the denominator, and what that would leave me with is 2x plus h minus 3. Wait, what's that mean? Nothing yet. This is just an expression that I can now take the limit as h approaches 0 of, because this expression is continuous at h equals 0. Change all the h's into zeros, and this turns into 2x minus 3. Then what do? Do I solve for x? What do I plug in? Nothing. This is your answer. F prime of x is equal to 2x minus 3. This is not one of those answers where you just are done when you get the answer. This is one of those answers where I really want you to think about what this means. This is so incredibly powerful. I can't emphasize it enough. This is saying that the slope of the tangent line to this function, f of x equals x squared minus 3x minus 2, at any value x is 2x minus 3. So if you were really interested in figuring out the slope of the tangent line to this curve at this point where x equals 2, you could just take this formula and change all the x's into 2's. From this expression, I know that f prime of 2 is equal to 2 times 2 minus 3, in other words 4 minus 3, in other words 1. But that's just one piece of information that this formula tells me. It doesn't just tell me the slope at 2, it tells me the slope at any point. Here's a graph of the function f of x. What I want to do is, on this same set of axes, I want to graph the derivative. F prime of x equals 2x minus 3. Maybe looking at this, you recognize this is a linear function, right? It's in the form y equals mx plus b. The y-intercept is negative 3 and the slope is 2. So I can graph this function. Let's see, it would go through this point, and then it would have a slope of 2. So it would go through this point. If I connect these 2 points with a straight line, I get this graph right here. You're like, whoa, that's not a tangent line. No, this is way more powerful. This tells you the slope of the tangent line at any point to this graph. The height of the graph in green gives you the slope of the graph in red. That's going to take a while to wrap your head around. Maybe it's easiest to demonstrate that with an example. Think about when x equals 2. Think about this point right here. There's a tangent line to this curve at this point. It looks more or less like this. What is the slope of this line? Kind of appears to be 1, yeah, because the height of this graph in green is exactly 1. Let me draw another tangent line for you. Maybe I'll draw a tangent line right here. It's going to be super steep. It's hard to even draw, but it's going to look something like this line in purple. How steep is this line in purple? Well, it's hard to tell by looking at the tangent line, but I know because the height of the graph in green is exactly 5, the slope of this tangent line right here is exactly 5. There's a point at 1.5 where the height of the green graph is 0. What does that mean for the height of the green graph to be 0? It means the slope of the tangent line to the red graph must be 0 at this x value. Oh yeah, if you look right here, it looks like the tangent line is horizontal and the slope of a horizontal line is 0. Anywhere to the left of x equals 1.5, like positive 1 for example, the height of the green graph is a negative number, so the slope of the tangent line to the red graph at that point would be a negative number. The graph in green encodes information about the graph in red. And eventually you'll get to the point where you can look at the graph in green and extract that information about the graph in red and see the connections between the two graphs. And that is incredibly powerful. Way more powerful than just figuring out the slope of the tangent line at one given point. Let's look at another example. It's a familiar example. F of x equals x cubed minus 2. We've done this one already. Except now we're not interested in figuring out f prime of 1 or 2, or I think it was 3 we looked at before. We want to know f prime of x. You can use the definition of the derivative or the difference quotient, whichever one you prefer. I suspect you'd prefer the difference quotient, so that's what I'm going to use. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. I got f of x, so I can figure out f of x plus h. It would just be x plus h cubed minus 2. And from that, I want to subtract f of x, which is x cubed minus 2. Be careful with your parentheses. We got two terms, so we need the parentheses to make sure we subtract them both. Divide that entire thing by h. Can't change all the h's into zeros. Got to cancel out this h down in the denominator first. Easiest way to do that is get rid of all the parentheses. X plus h cubed is kind of a pain to expand. If you feel the need, you could FOIL two of these together and then multiply that by the other x plus h, but I happen to know that that answer is x cubed plus 3x squared h plus 3xh squared plus h cubed, using a really cool relationship that involves Pascal's triangle that I'm going to teach you in the next section. For now, maybe just trust me that that's what you'd get. So these parentheses turn into this, but don't forget I have this minus 2 also. And then we have to subtract this term. This looks a lot like a 2. This is supposed to be a 3 here. It's x cubed minus 2. Anyways, to get rid of these parentheses, I take the negative and distribute it through. That makes that negative x cubed plus 2. And then I divide that entire mess by h. This looks like a mess, right? It's a huge disaster. But don't worry, things are going to clean up really nicely. How do I know they're going to clean up really nicely? Because this h has to cancel out. And in order for this h to cancel out, all of the terms up in the numerator have to have an h in them, meaning any of the terms currently up in the numerator that don't have an h in them better cancel out. Let's see if that happens. There's an x cubed right here, but there's a negative x cubed right here. There's a negative 2 right here, but there's a positive 2 right here. How convenient. Getting rid of all that stuff leaves me with these three terms. They each have an h in them. I can cancel an h from each of these terms with this h, and that would leave me with 3x squared plus 3xh plus h squared. I want the limit as h approaches 0 of this expression. That's easy because zeros are great in math. This goes away, this goes away. I'm left with just 3x squared is my answer. What does that mean? It means that if I'm interested in the slope of the tangent line to this curve at a point like, I don't know, 3, it's really easy to figure out f prime of 3. I just take this expression and change all the x's into 3's. This is f prime of x. It's a function. It's a machine that tells me the slope of the tangent line for any value x. So things like f prime of 3 are now super easy to figure out. I get the same answer of 27 that I got before. But really, that's not the important thing. The important thing is thinking about this derivative as a function in its own right. Let me show you the pictures. I got f of x equals x cubed minus 2 graphed down here. That's this graph. Maybe you recognize the graph of x cubed shifted down 2 units. And then I got the graph of 3x squared, which is my standard parabola stretched vertically by a factor of 3. That's shown in purple. The height of the graph in purple tells me the slope of the graph in blue at any given x value. You should pause and just stare at this for a while. This is amazing. This graph in purple and its relationship to this graph in blue is so important and so deep and so interesting. You could just stare at the graph forever, right? The height of purple is 0. Oh yeah, the graph in blue is flat. But the height of the graph in purple is never a negative number. Oh, right, that makes sense because the graph in blue is never going down. There's no x value where the tangent line has a negative slope. The steepness of the graph in blue gets bigger and bigger the further I go to the right and the further I go to the left. How much bigger? Well, it's completely modeled by this parabola right here, which is kind of cool. Here's a question to see if this is making sense to you. At this point right here, how steep is this line right here? What's the slope of that line in red? Do you know? If you're thinking, I think it has a slope of 3, perfect. Why? Because you're like, well, 1, 2, 3, it looks like 3. No. Don't estimate the slope of the tangent line by looking at my terrible drawing. Figure out the slope of the tangent line by taking advantage of what you know about derivatives. The height of the graph in purple is 3 when the x value is -1. Therefore, the slope of the tangent line to the graph in blue is 3 at this point where x equals -1. Our radical function, f of x equals 10 minus x square root. Suppose we want f prime of x. Maybe this time I'll use the definition of the derivative just to mix it up a little bit. It's the limit as a, our other point if you want, approaches x, the point that our tangent line is going to be at, of f of a minus f of x divided by a minus x. Change in the y's over the change in the x's. F of x is the square root of 10 minus x, so f of a is the square root of 10 minus a. From that, I want to subtract f of x, which again is the square root of 10 minus x, and then I divide that entire thing by a minus x. Maybe it's obvious to you looking at this that we can't just change all the a's into x's, or we get 0 over 0. I sure hope that there's some sort of trick. This a minus x has to cancel with an a minus x up in the top. It's not obvious how to find that a minus x up in the top unless you've seen several of the exact same examples where we employ this trick called multiplying by the conjugate. My first term here is the square root of 10 minus a. My second term here is the square root of 10 minus x. Currently, the sign in between them is a negative. What I want to do to create the conjugate is change that into a positive. If I'm going to multiply the top by that expression, I better also multiply the bottom by that expression, so I'm not changing the value of the expression. It's ugly, but it's about to get a lot prettier. Expand things out. Think FOIL. Square root of 10 minus a times square root of 10 minus a is just 10 minus a. The square root of 10 minus a times the square root of 10 minus x, I don't know what that is. It's a huge mess. Don't worry about it. It's the same as the square root of 10 minus x times the square root of 10 minus a, except that latter one is negative while that former one is positive. Get the exact same thing. One's negative, one's positive. Stuff all cancels out. All that's left is the L in FOIL, the negative of the square root of 10 minus x times the square root of 10 minus x. A negative times a positive is negative, and then the square root of 10 minus x times the square root of 10 minus x is just 10 minus x. Careful with your parentheses. Down in the bottom, don't FOIL this all out because it's the a minus x that you want to get rid of. Instead, leave the denominator in its factored form and hope that what you have up in the numerator is something that has an a minus x in it. Am I that lucky? Yeah, if you take the negative and distribute it through, this turns into a negative 10. The negative and the positive 10 cancel out, and this turns into positive x. So I have negative a and positive x. If I factor out a negative 1, I have positive a and negative x. In other words, a minus x. Down in the bottom, I also have an a minus x, and then I also have this square root of 10 minus a plus square root of 10 minus x. I get the really satisfying step where I cancel out the a minus x's. That's especially satisfying because I know it'll make this limit so easy to evaluate. I want the limit as a approaches x of negative 1 divided by the square root of 10 minus a plus the square root of 10 minus x. Evaluate this limit by changing all the a's into x's. I get negative 1 divided by the square root of 10 minus x plus the square root of 10 minus x. What's the square root of 10 minus x plus the square root of 10 minus x? Well, one way you can write it is it's 2 times the square root of 10 minus x. F prime of x, the derivative of f of x equals the square root of 10 minus x, is negative 1 divided by 2 times the square root of 10 minus x. It's not obvious at all that this function would have any relation to this function. They look really different, but if you graph them both on the same set of axes, you'll see some really powerful connections. The graph in red gives the slope of the graph in black. Earlier, what we looked at was f prime of 1, the slope of the tangent line to this curve when x is equal 1. We calculated that that's equal to negative 1/6. How's that show up on this graph? Over here in black, we have f of x. Down here in red, we have f prime of x, the derivative. If I tried to sketch the tangent line to this curve in black at this point where x equals 1, it would look something like this. What's the slope of that line that I just drew in purple? It's whatever the height of this graph is at this point. It's definitely a negative number. It appears to be about negative 1/6. In fact, it's exactly negative 1/6. Look what's going on with this graph in black. The further you go to the left, the closer it gets to horizontal. This red line is getting closer and closer to 0 here, which would signify a tangent line with a slope of 0, which is a horizontal tangent line. But as you work your way to the right over here and get closer and closer to 10, this graph gets steeper and steeper. At 9, for example, if we wanted to know the slope of this tangent line, poorly drawn, but it looks like it goes down 1 unit each time it goes right 2 units. I bet the height at this point right here is exactly negative 1/2. And then maybe interestingly, when we get to this discontinuity at 10, the graph gets closer and closer to vertical. Right? If we look super duper close to 10 at like 9.9 and tried to graph a tangent line there, it would almost go straight up and down, heading down as we go slightly to the right. So the slope would be some large negative number, which is what we see with this asymptotic behavior that the derivative has. But I don't want to get too lost in the details. The point that I want to make is the graph in red encodes information about the graph in black. And the information encoded in the graph in red is super important to the function pictured in black. I know this video is getting really long, but I want to do one more example. Maybe I'll even cut some corners. Leave this one as an exercise for you. See if you could figure out f prime of x. You can either use the definition of the derivative or the difference quotient, whichever you prefer. It might be a little bit easier to use the definition of the derivative here, but again, it's your choice. Cutting out a lot of steps, but I'll show some steps just so you can kind of check your work in case you're working this out on your own. I think what you'll find is that f prime of x, whether you use the definition of the derivative or the difference quotient, is negative 5 divided by 2x squared. Let's take a look at the graph of f of x equals 5 over 2x and the graph of f prime of x equals negative 5 over 2x squared on the same set of axes. That's kind of cool. In blue we have f of x, in red we have f prime of x. The slope of the tangent line to the graph in blue at any point that you want is given by the height of the graph in red. Pick on some examples, draw some tangent lines, investigate some different heights and slopes if you feel like it. That connection is kind of subtle and takes a while to wrap your head around, but it's really cool once you get it. One last thing that I want to leave you with. This is the last video that I made for this section, but there's this series of videos that somebody else made that are really good. This guy's YouTube channel is called 3 Blue 1 Brown, does some really cool, neat animations with math. And a lot of it is way beyond the scope of this class. But he has this one series called The Essence of Calculus, and I think it's something you might enjoy. It's a playlist, it's 12 or so videos, and you could watch them all if you want. But at a minimum, there's a few that I think you really should watch. So what I'm going to do is I'm going to start linking those videos on our page. This first one is interesting and all, but really it deals more with Calculus 2 than Calculus 1. I think the first video that'll be relevant to our class is this one called The Paradox of the Derivative. And I think by listening to somebody else who frankly makes videos way better than I could ever dream of making them, hence the 2.8 million views, will really help you get a deeper understanding of this stuff. The videos aren't super long, and they don't get into all the different details that we get into, but they kind of give you a high-level overview of this stuff with some really cool visuals. The next video that you'll see on our WAMAP page will be this video right here. A comment when you watch this video, he doesn't explicitly call it the difference quotient, but he's going to get into the difference quotient a lot. And instead of using the letter h as the difference between the two x values, he's going to use the symbol dt. The difference in notation might make it a little bit complicated for you, but just think, anytime you see that dt floating around, think that's our h. Hope you end up enjoying that video.